Hi, check out what just turned up on my bench. Whoa, look at it. Isn't it beautiful? It's a Electronic Development Corporation MV106J DC voltage standard. Look at all the knobs. I love it. Precision City. It's awesome. It's now done. I think it's owned by a company now called Krohn-Hite. They still sell it. It's still a current model. And I thought we'd turn it on, check it out, see if it still works, calibrate it, look at how it works, internal construction, teardown, bit of theory maybe, and should be fun. Let's go. And here it is. It comes in a rather old style aluminium rack size cabinet. It's got a little aluminium tilting bail like this, but it's also got another flip out tilting bail like that, which is really quite nice. I like it, and it's in fairly good nick. I'm not sure how old it is. I think it's the manual, which you can download, says it's last updated 1991, no, 2001, sorry. So it's like a 10-year-old model, but it could be based on older than that, because it seems quite old school with the old style rotary encoder knobs, but maybe it's been updated or something like that, I'm not sure. Full scale of 10 volts or 100 millivolts or 10 millivolts. It's three ranges. There is another type which has a current output as well, but this one doesn't now. The cowl sticker here, if you take a look at that, it's last cowled in 2007, so June 2008, and made in Boston, Massachusetts. Do they still make anything in Boston anymore? I don't know. I think they are. I'm sure there's a few things made there. Anyway, I quite like it. It's got the sense outputs as well, because when you're talking about a precision DC instrument like this, it's got to sense the outputs, but it does have little short-in bridging bars in there. If you're just hooking it up to a voltmeter, then that's fine. You don't need the sense outputs. They can just be tapped directly off the output, and you can just use a 2-wire instead of 4-wire. You can invert the output, nothing unusual there. And I love, it's got 6 decades here, and I love these style rotary selection knobs, and you'll notice I'm quite a fan of those. I've got quite a few of the Keithley instruments there. I've actually got 4 of those, and I just love those style knobs. So I love this thing. It's brilliant. And of course you can set, let's say we've got 10 volt full scale here. You can set 10.00001 volts. That's the resolution of it. Beautiful. It's 10 microvolts resolution on the 10 volt range, but if you go down to the 10 millivolt range, we're talking 10 nanovolt resolution. Wow. Nothing exciting on the back, I'm afraid, just the model number and a 240 volt selection switch. So it was 110, switched it over to 240, and we'll see if this sucker works. Alright, we'll just try it with my Fluke 87 here first. As I said, we've got the current sense input shorted with the current bars there. Ideally, if you had a big load, you would actually take the sense directly onto the load point itself for absolute accuracy. But in this case, it's going to be more than good enough. So let's switch it on and see what happens. Let's put it to 10 volts, and hey, it lights up overload. And yep, the overload LED is still on. Oh, no, there we go. It's gone out. Looks like it requires some settling time, perhaps. And bingo, there we go. 10.0000 volts, and we're pretty darn spot on, almost to the least significant digit there. So it looks like it works. Let's change it to 100 millivolts there. And, beautiful. Look at that, 100.00, spot on. And we've got 100.00. Well, let's whack this up one notch. That should give us one least significant digit. And it does. There we go. Changing one at a time. Wow, it's spot on. And of course, we've got 2 decades below that, which won't do a damn thing. But if we turn that up by 10, it should jump to 8. And it does. There we go. So it looks like it's going to still be, well, I'm not going to say within spec. It's within, you know, the 0.05% of my Fluke 87 here. But this thing has specs of, what are they? 0.003 or 30 ppm over the temperature range. Now this thing actually has specs of plus minus 0.003% or 30 ppm over well the span of a year, and 0.005% or 5 ppm per degree C temperature drift. So it's not super high end as far as DC standards go, but it's not too bad at all. It'll be a nice addition to the lab here, I think, just for a precision voltage source for testing meters and things like that. But it seems to work just fine. That's the 100 millivolt range, and we go down 10 millivolt range. Yep, not a problem at all. I like it. It's nice, and there doesn't seem to be any noise on the pots either. With these things, you've got to sort of, if you jiggle the pots a bit, you can often see if there's any issues there, but I can't see any problems there at all. So it seems to be working just fine. And we'll try the negative on there, and no, it's within, you know, that's pretty darn close, so that's not too bad at all. So I determined that this sucker is pretty much still within spec. Well, I'm not going to say within spec, because it's, you know, only within pretty, you know, it's pretty close to actually check its performance spec. It's going to need better gear than what I've got here, which is what we'll have to do later. But it basically works, so I'm pretty darn happy with that. Now I could check the linearity of it and things like that, but generally with these sort of things you don't have to, because the linearity is set by precision voltage divider resistors set up with these pots, either in a Kelvin or more popular format as the Kelvin-Varley configuration. So basically these things shouldn't drift unless those actual resistors drift, which generally doesn't happen too often. It's more likely that the voltage reference diode in there would drift or something like that, but even those are pretty darn stable. So I'm not surprised that this thing still works, because there's not much in them to go wrong. We'll find that there's only a power supply in there, a reference diode, an amplifier, and a bunch of precision resistors on these knobs here. Let's go one step further than the Fluke 87, shall we, and get my HP 3478A bench meter, which is actually going to have a similar short-term drift capability to this DC voltage standard, and we've got it set to 10.00000 there, and it's not too far off at all. But I haven't checked the cal in this in quite some time, and of course, you know, they have to come up to the same temperature, and well, it's a bit warm today here in the lab. It's probably 25, 26 degrees, maybe even 27 degrees C in the lab here. So, you know, it's not exactly ideal calibration conditions, but we'll fix that later. Now let's go down to 100 millivolts. There you go. That's not too shabby at all. Let's go down to 10 millivolts, and once again, not too shabby. I don't mind it at all. So, it might need, well, see, we don't know which one's out. We don't know whether my 3478A is out, or this is out, or a combination of both, or whatever. I'll have to take it to a standards cal lab to find that out. But if we can calibrate this baby, then we can use that as a transfer standard to then calibrate my 3478A. That'd be neat. Alright, let's open this sucker up and see what we've got inside. Now, as I said, what you're going to find that you'll get in here, this will be my guess, and I think I'm going to be pretty accurate, is that you'll find like an old school PCB with all through-hole components. Obviously, you'll have a power supply, mains power supply. You'll have a precision voltage reference, which will be like a zener, or you know, a buried reference zener temperature controlled, and it'll have a Kelvin-Varley divider on the front, and an amplifier, and that's pretty much all it is. It says it's got a chopper amp. I don't have the full manual yet, but I've asked for it, so that should turn up shortly, I hope. And let's pull it off and see what we get. Power's off. Yep. Hey, there we go. Ta-da! And that's not too far off at all. It's pretty much what I expected. Now, one of the first things I noticed though is that quite possibly this doesn't look like a Kelvin-Varley voltage divider arrangement. It just looks like a standard Kelvin voltage divider. And the giveaway there is that there appears to only be a single link between each decade bank there, not a dual link as you'd expect, and a more complicated switch arrangement as you'd expect on a Kelvin-Varley, which is what you'll find in my Keithley instruments over here. They use Kelvin-Varley dividers in them, but this one looks like it just uses standard Kelvin divider. We'll have to get the schematic to verify that, but there you go. Anyway, it's a whole bunch of very precise resistors on there. We'll have to check out the values. Some trim pots over here on the main decade. That's your first decade there, and it looks like it's got trim pots for all the various ranges. You've got a main board down here, and you've got a mains transformer. Now, one of the interesting things to note about the mains transformer here is look at all the exposed wiring here. It's there's no heat shrinking on that at all. It's all totally exposed, as is the switch on the main switch on the front panel, and that you wouldn't get that past these days, but yeah, it's past the safety standards anyway. And you'll see down here, this is the mains cable input, and there's like an insulated standoff there, which is just used to join the two wires, and once again fully exposed, so there's not really much put into the you know, internal safety of this instrument, but that's, you know, typical old school stuff. And your output jacks over there, they've got gold plated, you know, they'd be really good quality gold plated contacts and things like that, crimps, and going off, the wiring's reasonably neat and tidy, I guess. As for holding the PCB in place here, this is a very old school construction technique. They've got the aluminium plate with the cutout for the board, and the board screwed on the underside there, and they've just cut it out for the components. You'll see this construction method used quite a lot in these sort of rack mount early designed instruments. Now, one of the first things I'm looking for in something like this is, where is the voltage reference standard. Now, I've got this curious looking package here, and but I don't think that is the voltage reference. I get a feeling that that's not it. I'm not actually sure what that is as well, and at all. It's got two common terminals here. It's just a 4-terminal device, 2 pins on either side. There's an in, there's an out, but that's not what you'd expect in a temperature compensated buried zener reference, like in the HP 3478A multimeter we just had a look at. It's got an LM299 temperature compensated voltage reference in it, and that's basically just a buried zener diode that isn't very precise at all, and we'll go into this later, but it keeps it at a constant temperature. And I don't see, so if that was the voltage reference, I'd expect to see a heater connection on there, not just in and out. I'd expect to see you know, just the diode connection on one side and the heater on the other, but that's not it. But looking down here, they've got the reference down here, and that looks like it might be the reference diode. Let's go check that out. There you go. It's got EDC reference diode 4593 at 6.1730 volts at 6.5 milliamps current. So obviously they've, and because that diode is in those like soldered after this thing's assembled into those little contacts there, I reckon that is the reference diode for that thing. So I'm very surprised that it's not temperature compensated. I fully expected a temperature, you know, with 0.00, well, what is it, 0.0005 or 5 parts per million temperature coefficient, without getting that, without a temperature compensation on it, must be one hell of a good diode. So we're going to have to wait until we get the manual for that and see what part number it is. Now I've turned the power on, and let's see if we can actually measure that diode down in there, and if I'm correct, it should be 6.1730 volts. So let's give it a go. Bingo, 6.173 volts. It is. Now, as for the rest of the board here, there's no silk screen at all. Somebody's handwritten, you know, R4, R3, R2A, R2, R1 there. No silk screen. Really old through-hole kind of stuff. And these voltage regulators here, look at check out the pins. The spacing is not even on them. They've had to splay those pins out. That's, you know, that's a bit bodgy. I don't like that at all. And we've got a date code on this LM741 here of the 4th week 91. So there you go. That dates this unit to at least 1991. Now, of course, one of the things you notice here is this little daughter board here, and I'm going to assume that that's the chopper amplifier, because they talk about that in the manual. So, but it almost looks like it's a bodged afterthought, like they had to add it on. But if you actually wiggle it here, it should, looks like it will pop out, and ta-da, there we go. Look at that. That is, it looks like they've purpose designed that. It was actually designed. I thought it looked like a bodge board, but it's not. It looks like they actually manufacture that module as a separate thing. They probably manufacture and test it. I mean, there's no trim pots on there, but maybe they, you know, they test things. They actually select the components and put them on there or something. But yeah, it's all very old school, and I'm quite surprised at the whole thing. No Kelvin-Varley, at the impreciseness, really, of the whole thing. You know, they're not using a temperature compensated reference diode down here. They're not using a Kelvin-Varley divider, but hey, you know, they've got away with it. I'm sure it will meet its claimed specs. And you can see the precision resistors on the decade switches there. That's a 2K plus minus 0.005% precision resistor, and as you go, they won't all be that precise, but all the ones over there will be. Like the ones further down, you know, they don't have to be as precise, not necessarily as you go down, but at least some of them are at least 0.005%. And the ones down here on the first decade here, these are at 0.02%. They don't have to be as precise because each one of those is trimmed to its actual value. Actually, I just looked up that part number, the TSC 76552 there. That is actually a chopper stabilized amp. So there you go. And I've talked about chopper stabilized amps before. The reason you're going to use one of those in an instrument like this is that it has, essentially, it zeroes out, it nulls out any DC offset errors, and this is a DC precision reference. So what don't you want in this? You don't want any DC offset errors. Bingo, you've got to use a chopper stabilized amp for that. And thanks to Joe Inglis from Krohn-Hite, we've got the schematic for it in record time, and what can best be described as the manual. It's a bit of a hodgepodge, actually, the manual, but we do have the schematic. I'm not sure if it's actually, this is all they had. The model I've got is the MV106J. This just says MV106, so I'm not sure what's actually going on there, but anyway, it's pretty much what I expected, apart from the Kelvin-Varley thing and the temperature controlled zener. So let's actually take a look at it here. We've got over on the left side here, we've got our supply rails up here, and we've got, bingo, a constant current generator, which you have to, here's the obviously the zener reference diode here, and because to get a constant voltage out of a high precision, high stability zener diode, well, not high precision, but high stability, go into that later, zener diode, then you need a constant known current through it. So that's what this is designed. It's got an adjustment pot there, and you tweak the voltage, you tweak the current through the diode until you get the exact voltage you want, and then in theory, it should just stay like that, based on the temperature stability of the diode will be the main contributing factor to the drift of this absolute reference. So there's our voltage reference here. So a constant known current flowing, which is inside, it's actually labelled as 6.5 milliamps. So that you adjust that pot there, which is pot number 1, and they've labelled it pot number 1 on the board too. So that's handy. So we've got pot number 1, 6.5 milliamps through that zener, which gives that measured voltage drop, which you saw handwritten on the label inside the unit. So that's where all the stability comes from. Bit of bypassing across it there, and then we've got our decade resistor networks. There's the first decade there. Once again, it shows all those trim pots we saw on that board, if you remember. And then once again, it's this is the next decade, then the next decade, and as you can see, they do go down in steps: 20k, 2k, 200 ohms, 20 ohms, 2 ohms, and 0.2 ohms. So there you got your 6 decades. And as you can see, because it's not a real precision Kelvin-Varley divider, it's just a standard Kelvin divider, then you need these little trimmer. We've got little trimmer resistors here for the various ranges to just allow you to tweak the values there. And it's not the best drawn. All these range switches are quite complicated and convoluted, but pretty much the operation is pretty simple. There's our overload indicator down here. It's just a comparator, an LM741, which then drives the overload lamp here. And here's our chopper amp. So it's basically just a negative feedback, zero offset chopper amp, the gain of which is based on the feedback here. So it's pretty darn simple. And of course, there's a driver. They've got an emitter follower driver here, which drives the output. But apart from that, it's fairly simplistic, really. And it's obviously good enough for the job. If you tweak things and you design it properly so that it's low drift, well, it works a treat. And here's your output resistors down here, and as in the manual, it matched. Basically, it's got a 3K output impedance on the 10 millivolt range, and then the 100 millivolt range has got a 300 ohm output impedance, and then 3 ohm output impedance on the 10 volt range there. And if you grossly simplify this circuit, you end up with nothing more than a simple inverting amplifier here with a very low drift precision buried zener reference with a constant current source. And as you can see, the gain doesn't need to be very high because you've already got 6 volts here for the zener, and our maximum output is only 10 volts. So you only, you don't even need a gain of 2 here total. So effectively what you're doing is using this as a precision divider, and then these are your 6 decade knobs on the front like that. And of course, I've left out all the little trimmer things and stuff like that to actually calibrate the thing. I've left out the emitter follower driver and stuff like that, and the sense circuits. This isn't actually grounded here, but basically that is pretty much what we've got in here. It's very, very simplistic in its basic operation, but that's all it needs to be. What exactly is a Kelvin-Varley divider I've been talking about? Well, we have to start at the Kelvin divider. Now, you've seen this before. In fact, it is what you know as a voltage divider, what most people call a voltage divider, but its real name is actually a Kelvin divider, named after Lord Kelvin, obviously, you're probably familiar with. Now, this is what is used in this instrument here. You have, this is 1 decade, okay? You have a string of 10 resistors like this, and you tap off the various voltage that you need. And that's fine if it's just 1 decade. It's fine and dandy. These could be nice high values like 10K or something like that. Now, when you get to a multi-decade device though, like on this one's got 7 decades, as you saw. And really, when you get to that point, you can actually, when you put them in series, you would have another one here which effectively just shorts it out. So then you put multiple ones of these in series, okay? You would have one of these for each decade. So you'd have 10 resistors for each decade, and then they short out, etc., etc. But the problem with this, as you saw in the schematic for this thing, is that each decade must get progressively smaller in value by 10 times, an order of 1/10, an order of magnitude. Okay, so we've got our first decade up here is 20k, then it's 2k, then it's 200 ohms, 20 ohms, 2 ohms, 0.2 ohms. Now, you think, okay, what's the big deal? But, think about it. These are all mechanical switches in here. They all have, dirty contacts and, and they bounce around and do all sorts of funny things. And they're going to have a certain contact resistance, a certain minimum contact resistance. And really, if you, you don't want to start off with too high a value because then your thermal noise is too high and all sorts of stuff. So, but when you progress down like that, down to 0.2 ohms, you're right down in the territory of the contact resistance of all these switches. And it's not just this decade, but all of these other ones that you've got in series like this. Now you can of course make this work, as you can see in this instrument, but it's a lot of fiddling around, a lot of other adjustment pots you've got to have, a lot of mucking around, and if you've got dodgy contacts or contacts that increase in resistance with time or wear or whatever, then you're going to end up with all sorts of problems. So it's really not an ideal solution, and that's why lots of precision instruments will use a Kelvin-Varley divider. So let's take a look at that one. So to get around this problem, a clever dude named Varley, I don't know his first name, I don't know, I've never bothered to look it up, but it's known as a Kelvin-Varley divider, and it's, once again, it's a multiple decade system, as we'll see, but it doesn't use progressively lower value resistors, or it does, but nowhere near the order of magnitude drop for each decade that we saw on the Kelvin divider. Now, this is actually the internal schematic of a very high precision IET brand KVD 700 Kelvin-Varley voltage divider, and you can actually, it's in a box, you can actually go buy it, and they're really very high precision laboratory grade bits of kit for voltage division. Now, as you can see, this is a 7 decade one, so it has 0.1 ppm resolution. Absolutely incredible. That's 1 decade more than what we've got on our voltage standard that we're playing with here today. Now, as you can see, each decade, if you count up those resistors, it doesn't have 10 of them. It actually has 11, and that's one of the keys to this thing. Now, as you can see, it won't also have just a single wiper contact coming off here. It will actually have 2 coming off. There's 2 contacts like that that actually move in parallel like that, up and down. Now, the key to this is that because you've got 11 resistors here, okay, and you've got the contacts on a second contact point 1 over like that, then the rest of this, all of the rest of these resistors on the next decade, including this resistor here and this one and all the rest of them cascaded through 7, paralleled up through 7 decades like that, is actually equal to 20k, which then, when it's put in parallel with, in this case, the 2 10k resistors here, forms a 10k resistor. So those 11 resistors actually drop down to 10. So you're tapping off 1/10 of the voltage at that point. And that's the clever part about it. And likewise, it cascades through the system like that. These 2 wiper arms here move up in unison like that. So if they're up here, you would find that the wiper arm would be there and there, for example. Or right down the bottom, it'd be there and there. And you can tap off the same, exactly the same as the Kelvin divider we saw, tap off or dial up 1/10 for each decade, a value of 1, right down to, in this case, 7 decades, 0.1 ppm resolution. But look at this, the lowest value resistor in here is only 1k. So it's nowhere near the switch contact resistance that's going to cause an issue. So you can get, and you don't have to trim anything. So you can actually manufacture this thing and not really worry too much about your contact resistance at all, as you would in a traditional Kelvin voltage divider. So there you go. And you can go through and you can actually do the math of what values you need to put in parallel here. There's a 25k there and 40k there, and there's various configurations of it as well as on the output as well. It might have another divider on the output here, which will then tap off. There's various slightly little different configurations of it, but that's basically how a Kelvin-Varley voltage divider works. Very obscure, but very, very useful. Now let's take a look at the specs for this unit, shall we? It has an absolute voltage accuracy on the 10 volt range of 0.003%. That's actually, if you convert it, that's actually 30 ppm of the setting, of the actual setting you got. So if you've got 10 volts dialed in, it's going to be 30 ppm of that absolute accuracy. But you've got to add on another 5 ppm here. Basically, the difference between percentages and ppms is once you get below about 0.01%, it's a bit of an industry standard to start talking in terms of ppm, parts per million, instead of percentages. They're exactly equivalent, but it's just the industry speak, really. You're gonna, once you get into small stuff, it's a bit more professional to talk in terms of ppm, because it sounds more impressive and it's easier to work with than throwing in X number of zeros and things like that. Now we also have to add on 2 microvolts, and we have to do the math to figure out what that's actually going to be. And that's 5 ppm of the actual range, and the range of course down here is the full scale range of 11.111 volts. So if you work those out, 30 ppm of the setting, in this case we might use say 10 volts, and then we would have 300 microvolts absolute error there, plus we have to add on 55.5 microvolts because the percentage error of the range, plus 2 microvolts, a total of 357 odd microvolts. But one of the keys to something like this is the stability, and it's going to, good quality instruments will give you different stability over different periods. In this case, it's given you over a 1 day, 8-hour period of plus minus 0.01% or 10 ppm stability, so it won't drift any more than that over a period of 8 hours, and over the period of a year it's still fairly tight at 25 ppm, once again plus 2 microvolts. And even for the 10 millivolt range down here, it's actually identical, 0.003% or 0.0035% basically, plus the 2 microvolts. Now that, for a 10 millivolt range, that's going to be 10.00037 millivolts. So coming back to our unit here, if we've got it set to our 10 volt range here, then that means it's going to be 10.00037 or plus minus 37. That is its absolute value. So when you calibrate this thing, that's all it's guaranteed to be. So these last 2 digits, especially the last one, you're really getting down into the noise. Effectively, you can almost say it's not quite useless, because from an absolute accuracy point of view it is, but because you can actually dial it in there, its resolution can be handy. And as we've talked about before, that's the difference between accuracy and resolution. Just because your accuracy is not the same as your resolution doesn't mean the resolution isn't useful for various purposes. And the other thing of vital importance is the temperature coefficient here, and it's plus minus 0.0005% per degree Celsius. And if you translate that over to our dials here, it's 0.00005% per degree Celsius change. So if you're sitting in the lab and your temperature changes by 1 degree, you've effectively dialed an extra 5 onto that digit there. But that's going to be a maximum worst case value. It's most likely in practice going to be better than that, substantially better, but as always in electronics, you should take, especially when you're doing precision stuff and really serious work, you've got to take that worst case spec. Now, if you're curious to know what reference diode is used in this thing, I looked up the parts list for it, and it's actually a 1N821ARU. device. Now, it's available from different manufacturers. I don't know which manufacturer is the one used in here. It's most likely not a microsemi, but this was the best data sheet I could find for an equivalent second sourced part. Now, as you'll see down here, this is 0.0005% per degree C. And you probably recognize that because that is the temperature coefficient spec of this actual unit that's based purely upon the reference diode, as you'd expect. Now, one of the curious things that might puzzle a lot of people with something like this is that look at the reference value. It's plus minus 5%. It's got a huge tolerance, and that is the difference between absolute accuracy and temperature coefficient over here. You can design a high precision instrument like this, high precision, high stability, using a plus minus 5% reference diode because you're not relying on the factory or the actual manufactured absolute tolerance of this thing, because you calibrate it, you tweak those knobs, you dial it in. All you care about is the stability of it. So one with temperature, because and age as well as another thing, but let's not go there. But let's just talk about temperature itself. That's all you care about. As long as you've got a very low tempco, what's called a tempco or temperature coefficient reference device in there. In this case, it's a zener temperature compensated diode. Then, as long as this figure is really, really low, you keep that diode at the same temperature, or it's so low that it doesn't matter, then you can just tweak your circuit, adjust it, and bingo, you've got a high precision, high stability circuit. But the problem is you've got to actually have access to some sort of secondary or Cal Lab standard equipment to do the calibration in the first place. But if you've got that, as any good manufacturer does, then you can do it, not a problem. And if you're wondering what reference is used in the legendary HP 3478A multimeter we used before, industry standard bit of kit, it uses an off-the-shelf reference diode. In this case, it's which you can't get anymore, it's been obsoleted, but it's the LM299. And basically all it is, once again, as I mentioned, it's a zener diode in there. It's a buried reference, very high stability zener diode, just like the microsemi one used in here, except it's got a little internal heater inside the package which keeps it, and it's got some regulation circuitry for the heater in there that keeps it at a constant temperature. So if you've got it at a constant temperature and you've got a constant current flowing through your diode, not a problem. It's going to be very, very high stability. And let's look at the spec. There it is, plus minus at 2%, right? It's horrible. That's the initial tolerance of this thing. You buy it and it can be 2% out. It's useless, right? You can't use that in a precision 5-digit multimeter. It's hopeless. But look at the temperature coefficient. 0.0001% or 1 ppm per degree Celsius. Fantastic. So as long as you calibrate and tweak this thing, it'll stay stable. So getting back to our 1N821 diode here, it's available in various grades. In this case, we've got the top grade, which is the 1N829 ARU with the lowest temp code. But this is from Micro Semi. They would have, it's a second source, it's a multiple source part. They would have actually used, because this doesn't quite meet the Tempco spec of the unit, they've obviously got an even better device like this. Now I searched finechips.com and one manufacturer had this for $80, another one had it for $6. So, prices are all over the shop, and really they would have sourced a really high spec unit, probably binned and individually selected from a specific manufacturer, a very reputable manufacturer, not just left it up to their purchasing people to purchase it from one hung low in China or anything like that. Would have been very specifically spec'd and probably even binned for them, and they might have even done their own in-house binning as well. Now, here's some interesting stuff. We love curves, don't we? Curves, characteristic curves are brilliant. They tell you a lot. Now, in this case, it is the change in temperature coefficient in percent per degree Celsius based on the operating current or the constant current through that diode, and they specify it at 7.5 milliamps here, which it has the best. It's not actually 0, it's actually 0.005% per degree C if you read the notes down there. But if you operate it at any other current, then you're going to be elsewhere on that curve, and you've got to take that into account. Now, this unit here uses 6.5 milliamps, but as I said, it likely uses a diode from a different manufacturer. It might be slightly different, you know, who knows. They've taken into account everything's hunky-dory. The other thing to consider with your operating current, this is even more critical, that it doesn't actually change with temperature. Your operating current must stay stable, and here's why. Look, here is your change in your zener voltage in hundreds of millivolts, 100 millivolts, 200 millivolts per your operating current here. So if you're operating at 7.5 milliamps here, okay, you smack on 0, but if you change it, the operating current by just a smidgen, you know, 0.1, you can be out by, well, in this case, 100 millivolts and 6.5 volts, so what we are, 1.5%. It's massive, right? It's huge. That's not precision. That's, you know, $2 one hung low multimeter kind of, you know, accuracy. So it's critical, absolutely critical, that your operating current remains stable, and it remains stable over temperature. Otherwise, you're not going to have a precision instrument like this. It's critical. So that brings us back to our constant current circuit here. This is just as critical as the reference diode itself. This must put a very precise current through this diode. Once again, it doesn't matter the absolute value of it, because you can, you know, trim it to any value you want here, but it must be completely temperature stable. So they would have tested that circuit to the hilt and designed it so that it has as good a tempco as the reference diode itself, or possibly even better. Well, it's either that, or they've got some really tricky dick spec special buried zener diode in here, which doesn't actually change much on that curve, which maybe has a flatter characteristic curve like that. Who knows? You'd have to know the exact one and where they sourced it from and get the exact data sheet from it. But anyway, that current can be just as important. And I'm here at TrioSmartCal in the NADA Cal Lab, and we're going to check it out against a HP meter, and I've got Charles Holtham here, who you've seen last time. Hey, Charles.
What we've got here is a Hewlett-Packard stroke Agilent 3458A, which is basically the world standard in long-scale multimeters. And what we're going to do is take your box, which is actually at 30 ppm per year, has got about a test uncertainty ratio of about 3.5 to the standard version of this meter. So that's close enough to give you an idea of just how good
sounds near enough.
Your eBay purchase is.
So the uncertainty ratio is only, what, 3.5?
3.5 to 1. Ideally, we'd like as close to 10 to 1 as we can get. 10
order of magnitude,
But, you know, you haven't got that amount of money.
No, exactly.
Neither have we.
But this is good enough. Let's give it a go.
Let's turn it on.
Let's turn it on.
Let's have a look. We'll have a look at the reading at turn on. And then we'll let it warm up, and we'll come back in, say, 20 minutes or so and see how well it's stabilised.
Excellent. Well, let's have a look. What are we getting now?
So we're just hooked up, simple 2-wire high impedance system. So we'll turn it on. You've got an overload light come on there.
Yeah, it comes on temporarily until it...
Well,
there we go.
There we go. So at switch on, you've got well, you're better than 0.0001% already. So that's pretty good.
There you go.
So
that's not too bad at all.
Let's come back in about 20 minutes and have a look.
All right. What's the temperature in the room here?
That is 20 degrees plus or minus 1 degree. 20.
They actually specify its calibration temperature at 23. Is that like an older?
That's an older standard.
Older standard. The new standard is 20.
Yeah, we operate this one at about 20.
Okay, excellent.
Yeah.
Well, we'll come back later and see what happens. All right, we're back half an hour later, and what do we got, Charles?
We're back. Okay, well, what we've got is we're on the 10 volt range, and as you can see, we're on the 5th digit. So the 5th digit on the 10 volt range would indicate the parts per million.
Yep.
So 1 there would be 1 part per million. We've actually got about 3.5 parts per million error looking at this. So
absolute error, assuming that this is absolutely...
Assuming that this is right, and this is right. This is actually quite amazing given the fact that you bought this thing on eBay.
and it's within a couple of...
And it was last calibrated
2007.
in July 2007, so I think you got yourself a bargain.
A bargain?
Yeah.
Fantastic.
Don't go setting up a rival Cal lab with this now, will you?
No. Let's turn it down to a volt, shall we?
No, you will have to allow for stabilisation.
Yep, it will
these
actually...
things do take time to
stabilise.
stabilise.
We'll notice that.
But even so, this is pretty good. Yeah, you're about 7 ppm at the moment.
Yep.
7-8 ppm. So given that the spec's 30, it's pretty good.
I like it.
Yeah. Take it home and never turn it off.
Right, I'll leave it powered up 24/7, you think.
But you know, the thing is, with us old things, you know, the older that we get, the more stable we get, and the same applies to the meter, and the same applies to the calibrator. They burn in, and we just get better as we get older.
All right, excellent. Looks like it's spot on. I thought that we'd have to tweak a few pots, but obviously not.
No tweaking necessary.
No tweaking necessary. That's good enough. So I can now take this home, use it as a transfer standard to calibrate my HP bench meter, my 3478.
Yes, absolutely. Yeah.
Yep.
You could certainly do it for your voltage anyway.
1.8 ppm out on 10 volts range. Let's.
Well, you've got a little bit of drift.
There's a little bit of drift, but that's 9.
It's just insane.
I'll sell it to you, Charles.
Yeah, I'll give you. What did you pay for it? I'll give you double what you paid.
Double what I paid. All right. Oh, look at this. This is obscenely pornographic.
It's a good box.
It is a good box. I like it. I thought I bought the instructions on how to calibrate and everything, but we don't.
I don't think you need to.
I don't think we need to. Like this will eventually settle down. That's ridiculous.
Well, you've also got the settling time of the meter to take into account as well.
Exactly.
It depends if these switches here are actually just operating on a passive divider. So
they are just a passive divider.
If all you've got is a passive divider, you're going to
well,
see
actually,
the
it's
meter
not
settling
because
time.
it's a chopper amp.
Okay.
There's a chopper amp in there, and it's used in the feedback loop of the chopper amp.
Okay.
So, but it is a passive divider. So let's go to 99.999, 996. Ah, too good. I'm not even going to wait for it to settle. It's already too good.
It's too good for what you paid.
Not that I'm bragging. It's this is silly. It's linear too. I like it. Linearity looks excellent. And if we check out the 0 error there, because I've got the output actually switched off, let's switch that on, and it's increased a little bit, but that's a pretty good 0 offset error. I like it. Yeah, so we're really down in the noise here, because these digits actually match the digits here on the voltmeter. So it's, you know, it is fluctuating down in the noise there. We could dick around and try and actually get its performance a bit better in various ways, but this is actually a shielded test cable we're actually using here. But yeah, as you can see, it's, you know, you've got to not play around with it. And so we are down in the noise pretty much, but if we bump that up by 0.1, we don't see it yet. There we go. Okay, now we're starting to jump up. So 0.2, 0.3, and it's starting to not quite follow that, but you know, we are right down in the noise region where, you know, where thermal noise and stuff like that comes into play based on your connections and your type of metals and stuff like that. It can actually become an issue. So it's a bit of an art of measuring that low stuff, but if we go up in to the 100 millivolt range, then we can play around with that.